starting chapter 4 of this book right here, Generalized Linear Models with Examples in R, question 4.1. Okay, we're going to do two things here. So first we're going to write out the Taylor expansion, at least up to 3 terms, of the log likelihood expanded around beta hat. And then we're going to look at a different statistic, the Wald statistic, and rearrange it. And then we're going to get an expression, which is the log likelihood ratio, and show then that the Wald statistic is approximately equal to the likelihood ratio test when the difference between beta and beta hat is small. Okay, so for the first one here, so we're going to write the first 3 terms of the Taylor series expansion, expanded about beta. So first let's look at the log likelihood. Okay, so we can express the log likelihood. We can express the likelihood as like this, which is just the parameter of the data, which I'm representing here, given the parameters. And here I'm using a theta for generic parameters, but the parameters that we're dealing with are betas, but I'm just using theta as a generic placeholder. And so over all of the data, this would be the likelihood, right? So it's the probability of each data point given a particular parameter. Okay? And so to get the log likelihood, of course, we just take the log of all of this, okay? And so we get something like this, and depending on the particular form of probability of x given theta, this will look however it looks. All right. So now when we get here to the Taylor series, you can, if you're not familiar with the Taylor series, by this point you should be if you've looked at chapter 3. So I won't spend a lot of time on the Taylor series. And in fact, I think I'll just skip to the end. If you want a little bit of a lesson, go to Khan Academy and get a really good grip on it. And I think in chapter 3 we covered the Taylor series, so I will skip that for now. But just rush us to the answer here, that the log likelihood Taylor series expansion is approximately equal to the log likelihood at beta hat plus the first derivative of the log likelihood at beta hat times the difference between beta and beta hat, and then 1/2 of the second derivative of the log likelihood at beta hat times the difference squared of beta hat. Okay. Now, so you can parse through that for yourself, but the important thing here is that this term right here, the first derivative of the log likelihood, is 0. And so what we're left with is that the log likelihood just equals these terms right here, right? So this whole middle term drops out. So there's the log likelihood for us. The Taylor series expansion of the log likelihood for us. Okay, and so now we're going to rearrange the Wald statistic, and we're going to show that it's approximately equal to this thing right here, and we'll talk about what that thing is. And hence that the Wald statistic is approximately equal to the likelihood ratio test, log likelihood ratio test, when the difference between beta and beta hat is small. Okay. So first let's talk about this thing. So this is the log likelihood ratio. All right. So sometimes it's, I don't know, gratifying to see why that's a ratio. Okay. So if we had the ratio of 2 likelihoods, okay, here and here, well, if we took the logarithm of that, that would be taking the logarithm of a ratio like that is the same as taking the logarithm of the numerator and subtracting the logarithm of the denominator, and so we would get this. Okay, so that's the likelihood ratio, or log likelihood ratio, and then for reasons that aren't really important, but if you multiply this by 2, you get a chi-square distribution, and it's exactly a chi-square distribution when when the probability distributions that we're dealing with are normally distributed. Okay, so we multiply it by 2 and we get a chi-squared distribution. So this is the log likelihood ratio, and when we multiply it by 2, we're applying the log likelihood ratio test because we can compare that to a chi-squared distribution. Okay. All right, so that's one piece that we have on the table, and now we have the Wald statistic, and this is what the Wald statistic looks like. Okay, so it's the squared difference of the estimate for beta minus another beta, the null hypothesis or whatever, divided by the variance of beta hat. Okay, well, the variance of our parameter, as we're told in the book, is 1 over the information of beta hat. Okay, and so now I can just drag that information out here. Now I'm just multiplying by the information, and the information of beta hat is equal to this expression right here. Okay, so now we have just these two pieces on the table, and what we're going to try to do is to try to get our Taylor expansion to look something like our Wald statistic. Okay, and also that our Wald statistic looks something like the log likelihood ratio test. Okay, so remember that when we last look at the log likelihood ratio Taylor series expansion, okay, we had this. That shouldn't be ratio. That's the expansion. Okay, we had this right here. And so I'm going to just rearrange this thing. So I'm going to subtract the estimate for the log likelihood of beta hat over, and then I'm going to get rid of this pesky 1/2 by multiplying everything by 2, and we get this equals this over here. Okay. So now notice that this is very much looking like our expression here. Okay. And now when we look at the right-hand side, when we look at this right here, okay, remember that the information of beta hat is equal to the negative expectation of the second derivative of the log likelihood. Okay, so this inside this big bracket we have right here. Okay, well, now this term right here is 1 over the variance of beta j, and so then that means that this expression we can substitute 1 over the variance of beta j for this and get this, which is our Wald statistic. Okay, so I think that's what we're meant to show.